Okay, so last time we looked at the Pell equations, and the Pell equations, yeah. So the Pell equations, they are a Diophantine equation of this form for some k in the integers. So usually we're looking at the positive integers because for 0 and the negative integers, the Diophantine equation solutions are pretty trivial. So basically this is greater than 1, because also 1 is also trivial, so the difference of 2 squares. So we're actually going to look at the next case, so just the smallest number bigger than 1, which is 2, k equals 2. I actually want to study this case using techniques from algebraic number theory. So what we would like to do is, or to understand the solutions of this, we would like to factorize it. What could be the reason behind that? Like, what would be why would we want to factorize it in order to find the solutions of this? Well, because for other k's, for basically k equals 1, factorizing it actually does help. So for in the case of k equals 1, it's what gives us the answer. So if we factorize it in this case, and then we find all the numbers that are the divisors of 1 in whatever new number system we make in order to factorize this, then we've basically found, at least in part, all the solutions of this equation. So if that makes no sense, let's just carry on. So what we want to do is factorize this, and there is no way to do that in the integers. We can't factorize this in the integers or even in the rationals. We can't factorize this into two polynomials of degree 1 so that all the coefficients are rational. How do we, well, maybe you might want to try to prove that, but I won't prove it. But the proof is actually not, actually look, let's actually just do this one step, and then you'll see, and I'll explain why it's true. That I won't give a proof, but I'll explain why it's true. So what we're going to do is we're going to use the difference of 2 squares on this. So and then use the fact the square root of 2 squares to make 2. So like this. And so basically, this is what we see is up to multiplication by a constant. This is the only way to factor this polynomial. So since there is no number that we can multiply the square root of 2 by to get a rational, it is not possible to factorize this into a product of 2 rational polynomials of degree 1. So it's multinomials, isn't it? Anyway, that's enough about that. This is not what do you call it? Theory of rational numbers or whatever. We're not really looking at analysis. We're just looking at the algebraic properties. So one thing we notice is that there is some kind of symmetry in this, and that's a symmetry coming from the difference of 2 squares. But the symmetry we notice is like, so the square root of 2 can be plus or minus 2. In the case we switch square root of 2 for minus square root of 2, this equation basically stays the same. And so basically this is the next step, and what we want to do is we want to study numbers of this form. Okay, that is basically, if you know linear algebra, this is linear combinations of the number 1 and square root of 2. Okay, and this is in the field Z. Okay, and one thing we want to show is that these two are independent. That is, there is no A and B. Sorry, if there's A and B such that AB square root of 2 equals 0, then A and B are both 0. And this is pretty simple. You can probably see why this is true. This is true because obviously the square root of 2 is irrational. Obviously, I say as in the proof is well known, and yeah. And so these two are independent, and so this and these two span all these elements, all the elements of this form, obviously. I mean, yeah, obviously. So then this vector space, maybe we can write it like this if we want. Okay, over z. Maybe z. We can put the z here. Maybe like this. I'm not sure if there's standard notation, but otherwise we don't know what field we're taking it over. But actually, no, don't worry. Don't worry. This is fine. No, this is fine. Okay. So we've got this. And what we want to show is that we've just shown this is a vector space of dimension 2, just by showing linear independence. So the dimension of this is a vector space. So because it's a vector space on the integers of a dimension 2, this is isomorphic to Z2, which is the points of the lattice, and then we can add them in the usual way, like for example, we can add it like that, like that. We can add the points of a lattice. Okay, and then so these two are isomorphic because we can add it. We add these numbers in the same way, and we want to understand more properties of these numbers, these kind of numbers, and that's what we'll do in the next few videos.